Bienvenidos a esta sesión del Seminario Permanente de Teoría de Continuos e Hiperespacios. En esta ocasión tenemos el gusto de presentar al profesor Matsuhashi de la Universidad de
Yes.
Shimain. Tiene alrededor de 23 publicaciones en diversos temas de la teoría de continuos. Esta vez nos hablará de algunos temas sobre continuos descomponibles. Thank you very much, Professor Matsuhashi.
Yes, you are welcome. Thank you very much. Thank you for the invitation. First of all, I'd like to thank Professor David Meyer for giving me such opportunity. Today, I'd like to talk about some topics. And let me see. Can you see? Sorry. Can you see my?
Yes.
Yeah. Okay. Thank you very much. So today I'd like to talk about, as mentioned earlier, some topics on decomposable continua. So first, let me give some basic definitions. First, let me give the definition of decomposable continua. Maybe participants in this seminar are familiar with this definition. However, let me give the definition just. Let X be a continuum. Then X is said to be decomposable. X satisfies the following condition. X is said to be decomposable if there exists subcontinua A, proper subcontinua A and B of X. That X is equal to A cup B. If X satisfies this condition, then X is said to be decomposable. Also, X is said to be indecomposable. If X is not decomposable. We deal with topics on decomposable continua. Next, let me give the definition of D-continua. Let X be a continuum. We say that X is a D-continuum. If X satisfies the following condition, for each A and for each non-degenerate pairwise disjoint subcontinua A and B of X, subcontinua of X with A cap B is equal to empty set. There exists a subcontinuum C of X. The following two conditions. One, A intersects C and B intersects C. And two, A minus C is equal to empty set, is not equal to empty set, or B minus C is not equal to empty set. If X satisfies these conditions, then we say that X is a D-continuum. Now let me give an example of a D-continuum. For example, let X be the sine 1 over X continuum. Then X is a D-continuum. Let X be this continuum. Then X is a D-continuum. To prove this continuum is a D-continuum, maybe the most difficult case is if A, maybe the most difficult case is as follows. A is this limit bar, and B is this continuum. But even for this case, there exists a subcontinuum C. Then C is a subcontinuum C such that A satisfies this condition, and also C satisfies this condition. In this case, A minus C is empty. A minus C is empty. However, so we can see that the sine 1 over X continuum is a D-continuum. And also, let me give another example. consider the sign, double sign one, the 1 over x continuum. This continuum is not D-continuum. This continuum is clearly this continuum is a decomposable continuum. However, this continuum is not D-continuum. Because if A is this limit bar and B is this limit bar, then there does not exist a subcontinuum C of X, which satisfies the condition of the definition of a D-continuum. So this continuum is not D-continuum. This continuum is a D-continuum. Okay, so next let me give the proposition. Let me give a proposition. Every D-continuum is decomposable. Now, I give a proof. Assume X, assume X is not, X is indecomposable. Assume X is indecomposable, then, as is well known, there exists X has uncountably many components. So take A and B of X. Subcontinue. Such that A and B are contained in in different components, respectively. Then, in this case, we can easily see that there does not exist a subcontinuum. such that A cap C and B cap C are not empty set. And A minus C is not empty set, or B minus C is not empty set. In this case, there does not exist a subcontinuum C satisfying these conditions. So in this case, so X is not D-continuum. So as a consequence, we can see that every D-continuum is a decomposable continuum. Yes. We see that each D continue is decomposable. So this completes the proof. Okay, next, let me give the following result. This theorem is proven by Professor Espinosa and in 2020, about 3 years ago. There exists hereditarily decomposable chainable continuum. Such that X contains no D-continuum, no D-continuum. No D-continua. We proved this theorem about 3 years ago. To be exact, the continuum X was obtained by Janisevsky in 1912. Janisevsky, more than 100 years ago. He obtained this X as a hereditary on the arcless continuum. And we, Professor Espinosa and I, showed that this continuum has this property, namely X contains no D continua. So in particular, X does not contain any R. Later, I give a construction of Janisevsky continuum. Okay, let me give the following definition. Then X is, we say that X is a D star continuum. If X satisfies the following condition, A and B, for each non-degenerate pairwise dissonant subcontinua A and B of X, non-degenerate subcontinua. There exists subcontinuum. There exists a subcontinuum C of X. Such that C satisfies the following two conditions. One, A cap C and B intersect C. And B minus C is equal, B minus C is not equal to empty set. If X satisfies this condition, we say that X is a D star continuum. Compare this definition to with the definition of a D continuum. So the difference between the definition of D star continuum and D continuum is only this part. D star continuum is the definition of D star continuum is this, and the difference between the definition of D continuum and D star continuum is only this part. Okay, next let me give the definition of a D star continuum. We say that X is a D star continuum if X satisfies the following condition. For each non-degenerate pairwise disjoint subcontinua A and B of X, there exists a subcontinuum C of X. Such that one A A cap C and B cap C are not empty set, and A minus C is not empty set, and B minus C is not empty set. If X satisfies this condition, then we say that X is a D-star continuum. Also, the difference between the definition of a D-star continuum and D-star continuum is only this part. So the definition continuum and D-star continuum, they are very similar. Now let me give examples of these continua. Before it, let me talk about the relation between the continua. What I have talked about so far, which I have talked about so far. First, arcwise connected. Arcwise connected continuum. Arcwise connected implies D-star. And D-star implies D-star star. And D-star star implies D. And D implies decomposable. Implications hold. Okay, and next, let me give examples of D-star star continuum, D-star continuum. First, let me give an example of a D-continuum which is not D-star star. In fact, sine 1 over x continuum. This continuum is D, however, not D-star star. To see it, for example, let B be this continuum, and let A be this continuum. There does not exist a subcontinuum C joining A and B minus C is not empty set. If C intersects A and both of A and B, then B minus C is empty set. And also, now let me give another example. This is double partial circle. this continuum is a D-star star continuum. This is not, this is easy to see. And this continuum is not D-star. Because, for example, let A be this continuum. This is the limit of this sine 1 over x continuum. And let B be this continuum. This is also the limit of sine 1 over x continuum. Then, if C is a subcontinuum of x joining A and B, then A minus B is empty set or B minus C is empty set. For example, like this. In this case, A minus C is equal to empty set. So this continuum is not D star. Okay. Continua. In fact, Professor Espinosa and I obtained the following result. There exists hereditary let me see. Hereditary D-continuum. Hereditary D-continuum. Hereditary D means each of its subcontinua is a D-continuum. Hereditary D chainable. Continue. Such that X contains no D star star continuum. As in the previous theorem, also this theorem, to be exact, this theorem is essentially prove this X is constructed by Janicki. More than 100 years ago. There are kinds of Janicki continuum. And as mentioned earlier, this X is essentially constructed by Janicki, and Professor Espinosa and I showed that this continuum has this property. So in particular, this continuum is hereditary D, so hereditary decomposable. X contains no D star star continua, so X contains no arcs. Okay, so considering the results so far, First, as mentioned earlier, there exists a hereditarily decomposable chainable continuum such that X contains no D-continua, and there exists a hereditary D chainable continuum such that X contains no D star continua. So I think to ask the following question. Is there hereditarily D star chainable continue containing no D star continue. I think it's natural to this question. It's natural to ask this question. And in fact, by the following theorem. This theorem is proven by I and Matsuhashi and Oshima in this year. Oshima was he was my student, and in fact he works at the same university as me. He is an assistant professor. Let X be a continuum. Then following are equivalent. First, one, X is hereditarily arcwise connected. Two, X is hereditarily and 3, X is hereditarily D star means each of its subcontinua is D star, and X is hereditarily D star star. D star star. These conditions are equivalent. So by this theorem, the answer to this question is no, because hereditarily D star star continuum is hereditarily arcwise connected. So such a continuum must contain an arc. Okay. However, recently we have obtained a strange D-star continuum. So I will talk about it. But before it, let me give the definition of a Wilder continuum. Let X be a continuum. Then we say that X is a Wilder continuum. Wilder continuum. If X satisfies the following condition, for each pairwise distinct points X, Y, and Z, these X, Y, and Z are pairwise distinct. There exists a subcontinuum C of X. So that C satisfies the following conditions. One, C contains X, and C contains the only one of Y and Z. In other words, the cardinality of this intersection is equal to 1. If X satisfies this condition, then we say that X is a Wilder continuum. Wilder continuum was introduced by Wilder in 1968. And in fact, to this theorem, we can add the following condition. X hereditarily Wilder. So this means each of its subcontinua is Wilder continuum. So in fact, Wilder proves that the equivalency between the condition 1 and condition 4 and as mentioned earlier, I and Oshima and I proves that the equivalency between the condition 1 and condition 2 and condition 3. Okay. Now, let me talk about the relation between these continua. First, arcwise connected. This implies Wilder and D-star. And Wilder does not imply D-star. And also and D-star does not imply Wilder either. And Wilder implies D-star star, This is easy to prove. And clearly D star implies D star star. And D star star implies D. And this is clear. And the property of being D implies decomposable. Now, let me give an example of Wilder continuum, which is not D star. In fact, example. The double Warshaw circle. This continuum is Wilder. This is easy to prove. However, not D star. And so, as mentioned earlier, Wilder does not imply D star. And also, let me give another example. This is a simple closed curve. And let consider this continuum. Consider this continuum. Then this continuum is D star. However, not this continuum, not Wilder. So, as mentioned earlier, D star does not imply Wilder. Okay. Now, let me introduce the following result. So, there exists D star star such that X contains neither Wilder continua nor recently we obtained this, we constructed this strange continuum. To construct this X, we used an idea of the construction of Janisevsky hereditary decomposable arcless continuum. So to talk about the excuse me, sorry. To talk about to talk about the idea of this, to talk about the idea of the proof of this theorem, let me talk about the construction of he obtained hereditary decomposable, chainable, arcless continuous an arc. Let x1 be discontinue, and let d1 be this point. He continued blowing up countably many points like as follows. First, let x1 be discontinue and let d1 be this point, and then blow up d1 to an arc like this. First, he blew up d1 to the arc. And let x2 be discontinue. And let f1 be the map from x to x1 to x1. So this limit bar, this is the limit bar of over sine 1 over x continue. This limit bar is f1 inverse of d1. Also, to obtain x, this is x2 and f1. And to obtain x3, we blow up d2 to an arc. And if d2 is this point, it's easy to blow up this point. Then x3 would be like this. However, if d2 is this point, if d2 is this point, then blowing up d2 is more difficult. Maybe x3 would be if D2 is this point, then blowing up D2 will produce the sine 1 over x continuum here. Like this. Sorry. Sorry, please wait. So, I have recovered. Yes, to blow up D2, maybe X3 by blowing up D2 to an arc, X3 would be like this. This is sine 1 over x continuum, and this line would be drawn into as it gets closer to where we blew up. This is X3, and also F2. So this limit bar is F2 inverse D2, and let F2 be the natural projection. And continuing in this fashion, we can obtain coordinate spaces x, coordinate spaces xi and bonding maps fi. And as the inverse limit of xi and fi, we can obtain hereditary decomposable arc-like and arc-less continuum. It is called Janicki continuum. And however, in our case, instead of blowing up points to arcs, in our case, blowing up points please wait. Let me see. In our case, instead of blowing up points to arcs, in our case, blowing up points to this continuum. And let x0 be this arc and let d0 be this point, and blowing up d0 to this continuum. And we continue blowing up countable many points to this continuum. And as the inverse limit of x contain d star star continuum containing neither Wilder continua nor D star continua. Okay. Finally, I will talk about relations between these continua and Whitney property. Maybe almost all participants in this seminar are familiar with the notion of, or let me omit the definition of Whitney property, Whitney reversible property. Being this theorem is proven by Oshima and I in this year. Being D star, D star star, and Wilder they are all Whitney properties. These properties are let me see. Whitney properties. And recently, we proved the following result. Being Wilder is not a Whitney reversible property. So being wider is not a Hoyton reversible property. In fact, consider this continuum. Let X be discontinuous. Then X is not wilder. However, each Hoytony levels of this continuum, each positive Hoytony level of this continuum is not a wilder continuum. So being wilder is not a Hoytony reversible property. And at last, finally, I give some questions. Question. Is being, not questions, question. Is being D or D star or D star star a Hoytony property. At the moment, we don't know the answer to this question. Okay, and that's all. Thank you.
Thank you.
Thank you very much.
Thank you. Is there any questions? I have a question. In other hyperspaces, are studied these notions?
Sorry, could you be sorry?
In which hyperspaces these notions are studied?
These notions are what? Sorry?
D star, D star, and wider.
So I'm sorry. I'm not. Could you repeat? Sorry.
Okay. Do you know if symmetric product of a continuum is a D-continuum or D star continuum or D star star continuum? The hyperspace of finite subsets.
Hyperspace of finite. So you say you have talked about the FNX or something like that.
Fn of X. Exactly.
Fn of X. I've never investigated about FNX with respect to D continuum, D star continuum, D star star continuum. However, I think it's interesting to investigate about the property of being D or being D star or being D star star in Fn of X. I think it's interesting problem.
Okay, thank you.
Thank you.
Is there any questions? Another questions? Okay. Thank you very much.
Thank you very much,
Professor Matsuhashi.
Thank you very much. Thank you very much. So can I exit?